We're going to talk now about inner products, and in particular positive definite inner products. But I want to start by summarizing the different kinds of matrices we've been talking about. So we started off talking about symmetric matrices, and the definition is, of course, x equals x transpose. And I want to emphasize that the meaning of this is captured by this equation. XVW is equal to VXW, because if you write these two things out, you see here on one side you have an x transpose, and on the other you just have x, and so those two things must be equal. And the eigenvalues of a symmetric matrix are real, and it can be diagonalized by an orthogonal matrix. Now, another thing we've talked about is orthogonal matrices, which satisfy this. And I talked about the fact that what this means is that it preserves the inner product. QV, QW is equal to VW. And again, we know about the eigenvalues. They have absolute value 1. And again, it can be diagonalized by an orthogonal matrix. Okay, I'm just going to put up the complex versions of these and not go over it in detail. We've been through this several times, but symmetric becomes Hermitian and orthogonal becomes unitary, and you put the appropriate bars in various places and you get the complex part of this table. And the last thing that we talked about was normal matrices, and I'll put them in here. You don't know anything in particular about their eigenvalues, but the main point is they can be diagonalized by a unitary matrix. Okay, now you might have noticed that there's something I skipped, which is the following. If x is symmetric, we talked about the fact that you can find an orthogonal matrix such that Q transpose XQ is equal to D. And I have the transpose here on the Q, not the inverse. And similarly, the complex version of this, if x is Hermitian, then you can find a unitary matrix such that U bar transpose XU is diagonal. And this is what we're going to be talking about now. You might say, what's the big deal? The fact is, if Q is orthogonal, then Q transpose is Q inverse. So that first thing is just saying Q inverse Q is equal to D, and we already knew that. But you should sort of ignore this fact. The point is that we're thinking of a symmetric matrix now in a very different way. I mentioned this earlier, and let me talk about it again. If you have a symmetric matrix, one of the main things it does for you is it gives you a new inner product. So let's go over that again. Remember, the usual inner product is just the dot product, or V transpose W. But if you have a symmetric matrix, you can define a new inner product, which I'll denote with the subscript x, by putting an x in the middle of this. And this is one of the main reasons we're interested in symmetric matrices. Notice that the thing that I get, if I change the order of V and W, I get this calculation. I'm allowed to take the transpose here, and I see that if I change the order, I get the same thing, provided x transpose is equal to x. So this is exactly the condition you need for VW to equal WV. All right, so before we dive in and talk more about these inner products, let me illustrate the difference in point of view here one other way. Suppose you have a linear transformation A given by a matrix A. You can change basis. And what happens when you do that? Well, you replace the matrix A with S inverse AS. That's a similarity transformation. Now, what if you're given a symmetric matrix X and you're thinking of that as giving you an inner product? What happens if you change basis now? What happens is the new inner product is given by S transpose X times S. That's a different operation. And in the setting of inner products, it's the one we need. And one comment I'll make is that if X is symmetric, then S transpose X times S is automatically symmetric, because you just check. When you take the transpose, you get this thing, and that indeed is equal to itself. So in the setting of linear transformations, the change of basis, you're getting the same linear transformation in a different basis. And the corresponding thing here is that we're getting the same inner product, but again, with respect to a different basis. All right. I think I've hammered home that point sufficiently. I want to go on now and talk about some properties of inner products that we have not discussed before. And it's the following. So let's take our symmetric matrix. Now, we have the usual inner product, VW is V transpose W, or this new inner product, V transpose XW. In what ways are they different? Well, one thing is, if you write this out and you look at the inner product of a vector V with itself, you get the sum of the squares of the coordinates. And of course, that's greater than or equal to 0. Now, with this new inner product, is that same true? Is the same property true? Well, obviously not. Let's just write down a very simple example. You take 1 minus 1. And if you take the vector xy and you compute its inner product with itself, what do you get? Well, you get V transpose x V looks like this, and that's x squared minus y squared. And of course, that can be negative. And it can be 0 even if the vector is not 0. And in some ways, we don't like this. So let's make a definition here. A matrix is said to be positive definite if the following condition holds. A symmetric matrix, I should say. If when you take the inner product of a vector with itself, it's always greater than 0, except of course for the 0 vector. Now note that I'm not saying that all of the entries of the matrix are positive. That's not what the positive definite condition is at all. So let's look at an example. Well, let's take a symmetric matrix, A1 through AN. Then if you take the inner product of a vector V with itself, you get A1 x squared plus dot 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 AN x squared. And the x squareds are all positive. So when is this positive definite? Of course, all of the AIs have to be strictly greater than 0. All right, well, that's easy enough. And of course, thinking a little more abstractly, I'm saying that the eigenvalues are greater than 0. Okay, now here's a word of caution when you think about non-diagonal matrices. Back in the world of linear transformations, if you replace a matrix A with a similar matrix, it has exactly the same eigenvalues. Different eigenvectors, but the same eigenvalues. Now, what if we replace a symmetric matrix X with C transpose XC? Does that have the same eigenvalues? Well, certainly not. There's no reason that it should. If C is equal to Q, then it's true because Q transpose is equal to Q inverse. But C is here is an arbitrary matrix. It's not required to be orthogonal. So let's look at an example. So I'm considering this operation X goes to C transpose X. Suppose X was diagonal and C was also diagonal. All right. Well, what does this do? Not much, but it does do a little bit. If you do C transpose XC, you get the B's and the A's, and then the B's again, not the inverses, but the B's. And so what you get is you're replacing each term you're multiplying each term by BI squared. So you're definitely changing the eigenvalues, but by a positive number. This is the crucial point. This operation, it doesn't preserve the eigenvalues, but it does keep their signs. So that says, in other words, that X and C transpose X times C, the eigenvalues, which are real, of course, all have the same signs. Okay, so the conclusion is the following. We have a symmetric matrix X, and we conclude that it's positive definite. Well, X being positive definite doesn't change if you replace it with C transpose X times C. And the reason is that the eigenvalues of both of those matrices, while not necessarily equal, they have the same signs. All right, fine. So here's a question. How do you tell whether a matrix is positive definite? Well, of course you can compute its eigenvalues, but that's hard. You don't want to have to do that. So what I would like is a test for a matrix being positive definite that without computing its eigenvalues. Okay, well, let's look at the 2 by 2 case. Suppose you have a 2 by 2 symmetric matrix. So that is to say A, B, B, C. That's a misprint. The lower right-hand corner is supposed to be C. How do you tell if this is positive definite? Well, if you compute the inner product of the vector xy with itself, you get this expression. And the way you tell whether this is positive is to complete the square. And I'll skip the details, but if you complete the square, you get this. A times the quantity x plus b over a y squared plus c minus b squared over a. And I'd like to know if that's positive for all x and y. Okay, let's stare at this for a minute. So I'm allowed to vary x and y as much as I want and try and make this expression negative. Well, let's see. This thing over here is some fixed constant. Doesn't depend on x and y. So, okay, this term here obviously does depend on x and y quite a bit, and it's positive. So suppose a was negative. Well, then if you took x and y really big, 1,000,000 or something, then you have a times something squared plus this constant. And if a is negative, if that something is big enough, this number is certainly negative. So there's no way that this is positive definite if a is negative, so we need it to be positive. And I'm going to punt on the issue about a being equal to 0. A is required, in fact, to be positive. So let's assume that. Suppose a is positive. Does that do it? Is this thing guaranteed to be positive? Well, this first term is a square, so that's good. But the second term is not. The second term might be negative and might cause trouble. In fact, if you chose x and y appropriately, you could make the first term equal to 0. And so if the second term is negative, you're definitely sunk. So you definitely need that the second term, c minus b squared over a, is positive. And let's multiply this thing by the positive number a, which we're allowed to do, and we get AC minus b squared is required to be positive. That's the determinant. Well, that's interesting. So what do we conclude? If you have a 2 by 2 symmetric matrix like this, the condition for it to be positive definite is the following. First of all, A has to be positive. And second of all, the determinant has to be positive. And of course, that's a very easy thing to check. It's much easier than computing the eigenvalues. And this is a special case of the following big theorem. Suppose X is an n by n symmetric matrix. There's a nice test for whether it's positive definite. X is positive definite if and only if the following condition holds. The determinant of mi is required to be positive for all I. And what I is it's the so-called minor. It's the matrix that you get by taking the upper left-hand corner of the matrix, and it's allowed to be of any size, 1 by 1 up to n by n. All of those determinants are required to be positive. There's n of them. And in the case of a 2 by 2 matrix, there were 2 to check. So let me restate this matrix. There's actually a little bit more content to it. So I'll restate it as follows. The following conditions are equivalent. Every one of these things is exactly the same as each of the others. The first one is that the matrix, a symmetric matrix, is positive definite. Okay, the second condition is that VV is greater than 0 for all V non-zero. Well, that's exactly the definition of positive definite. The determinant of all the mi's are greater than 0. There's n of those, I running from 1 to n. And all of the eigenvalues are positive. They're real numbers, of course, and they're required to be positive. And then the last thing is that all of the pivots of the matrix are required to be positive. So remember pivots? Well, they're much easier to compute than eigenvalues, so it's very nice to have a test for positive definite using pivots. Okay, that's a good place to stop. I will see you next time.